Okay, so here we look at a sample problem. So a 1.5 microfarad capacitor is charged to 57 volt. The charging battery is then disconnected and a 12 millihenry coil is connected in series with the capacitor so that LC oscillation occur. So what is the potential difference? VL across the inductor as a function of time. So this circuit is like LC in series with the I don't think we have a battery here, so it should be like this. So this is 12 millihenry. This is 1.5 microfarad, and the capacitor is charged to 57 volt at the very beginning. So it asks you what is the VL. What is VL? So of course we have d squared q d2q dt2 plus 1 over LC. Q equals 0. So this is the standard LC oscillation. And of course the solution will be Q equals capital Q cosine omega t. We can just skip plus phi because we do not care about the reference time, so we can just skip, just take phi equals 0 here, just for simplicity. You can just take arbitrary phi, maybe you can take a pi over 4, pi over 2, pi, 2 pi, whatever you like, but it doesn't really matter because we don't care about the timing in this problem. So so Q should be CV. Q should be CV, and it is 1.5 times 10 to minus 6, 1.5 microfarad times 57 volt. So this is 8.55 times 10 to minus 5 C coulomb. So this is the maximum charge at this node, or charge on the capacitor. So next we can really calculate the VL. VL. So this is Q. So we can have I in this direction, and of course VL following this direction should be like L di dt, and I is of course dq dt, and we know I equals dq dt. So this is nothing but L d2I dt2. So it should be L, and then we take the second derivative of Q cosine omega t, and of course Q is a constant, so we have a LQ, and then the second derivative of cosine will be minus cosine, because take the first derivative will be minus sine, and then minus sine take the derivative will be minus cosine. So we have minus cosine omega t, and then we also need the chain rule, which means we need to take the derivative of the argument and then take the square because we have a second derivative. So taking the first derivative here will be omega. So we have omega squared here. And of course omega omega is 1 over square root of LC, which means omega squared is 1 over LC. So we have minus LQ times 1 over LC cosine omega t. So we have here L cancel, Q over C is actually V. So we have minus V cosine omega t. So which is nothing but minus 57 cosine omega is t over square root of LC. L is 12 milli. 12 times 10 to the minus third power times C. C is 1.5 times 10 to the minus 6 power. So it turns out to be minus 57 cosine 7,500 T. And then the SI unit is to be volt because it is a potential difference. Potential difference. And so this is the answer of this question. Any questions? So for part B, what is the maximum rate di dt max at which the current I change in the circuit? Change I. Yeah, so of course we will have I to be dq dt. And of course Q is nothing but Q cosine omega t. And taking the first derivative will be minus omega q sine omega t. Yeah, so still we need to take the first derivative because we hope this we hope to find the maximum of di dt rather than I. So we have a di dt by taking the first derivative of this one, which is d dt minus omega q sine of omega t. So we will have minus omega q, and then the first derivative of sine is cosine omega t, and then the chain rule we need to multiply by another omega, so we have square here. Okay. So as much as we hope to find the maximum of this one, and this is a constant, this is a constant. So cosine omega t is smaller or equal to 1 or larger or equal to minus 1. So which means that di dt max should be omega square q. This is cosine omega t equals -1 to cancel the minus sign, so it will take the maximum value. Yeah, so this is 1 over LC and then times Q is CV. Q is CV. Of course, omega is 1 over square root of LC, so take the square will be 1 over LC. So times Q equals CV. So we have V over L. V over L. So it is 57 over 12 times 10 to minus third power. So this is 4,808 per second. 8 per second. Yeah, so the SI unit is like we have di dt here. So I is has a SI unit of A and T has a SI unit of S. So we can consider the SI unit like this way. Okay, so any questions? Okay, so next we consider a slightly complicated situation, which is the damped oscillation in an RC circuit. So rather than having only LC in series, we also have this resistance, which will actually dissipate some of the energy stored in this system. So here, to analyze the oscillation of this circuit, we write an equation for the total electromagnetic energy. So like the previous case, we also have a total EM energy will be U equals UB plus UE, which is this one. So I don't repeat because we have already discussed about this part in the last lecture. So now, however, this total energy decrease as energy is transferred to the thermal energy. So the rate that transfer is this one. Yeah, it means that the power dissipation of a resistor is P equals I square R, or maybe you can write it as a V square over R or V times I, whatever you like. These three are actually the same for a resistor, but actually it's use this equation here. So actually the power dissipation for this resistor is I square R, which means that P is actually dW dt. And you know the work done is actually the minus sign to the potential energy. So we have a du dt to be the minus I square R. So we have this equation here. Okay, so we can also take the derivative of U, so that on the left hand side we will have which means that the du dt will also be equal to this term plus this term. Yeah, if you don't know why, you can check back the last lecture. So we have derived the first derivative of these two terms will be the first term here and then the third term here. And it will be equal to this one. It will be equal to, yeah. And so of course we will have L over 2 and then 2I times di dt plus 1 over 2c times 2q times dq dt equals minus dq dt square R. Yeah, something like this. Yeah. Yeah, so actually this I is dq dt, and then this is the second derivative, and then we can just actually cancel these two, these two, these two, these two. Yeah, and then this I with this dq dt, and then one of the dq dt. So, and then we can just divide L on both sides or actually divide out on both sides. Divide out on both sides. So we can also multiply by the 1 over r on both sides. So we will have this is the no, we should divide by L. Yeah. So actually this one is the second derivative term, which is this one, and then divide by L, so we have R over L times QT, and then move it to the left side, so we have a plus sign here. And then this is Q, so we divide by LC, so we have 1 over LCQ equals 0 here. So actually we can derive this one. So different from the previous case, we also have this term, rather than just have the second order term and the 0 order term. We also have the first order term, so that this is still a second order linear constant coefficient ODE. So yeah. And of course, for this one, the solution will be this case. We have exponential function, cosine something. And then this cosine prime is not 1 over LC anymore. For here, for this expression here, we have omega square, which is 1 over LC. But here we need to subtract something, so which is not so trivial to you, but actually we can still derive it. And yeah, this expression is not it's familiar because we have already talked about how to solve the second order ODE. This is one of the cases. So here, let's see how to derive it. So let's see here. So we can say this is V, this is VR, this is VL. So I define the direction. It will be like this is minus sign, this is plus sign, and then this is minus sign, this is plus sign, this is minus sign, this is plus sign. So when we add these three together, it will form a whole loop, so which should be 0. So by using the KVL, we have a VL plus a VR plus V equals 0. Of course, you can say this is VC, but yeah, let's just use V here. Okay, so as much as we know this is V, so we can know the current. Actually, this is the same loop, so the current going through this capacitor is also the current going through this resistor, is also the current going through this inductor. But actually we can use this capacitor, so we can write I equals C dV dt. And also, as much as we know the I, so this is also the I. So using this inductor, so we will have VL equals L di dt. And of course, for the resistor, it only needs to follow the Ohm's law, so which is the easiest one, which is VR equals R times I. And of course, we can just plug in this one into here. So we have a LC d2I dt square. And then for this one, we have RC di dt. So this is the potential method. Here it is the use the power method. It use the power method or the energy method mentioned in this textbook. So here, usually in cycle theory, we use the potential method, use KCL, KVL all the way to write out the equation. So in this case, we can substitute this one, and 1, 2, 3 equation into here. So we will have VL is LC D2I dt2, and then plus VR is RC di dt, and then V is sorry, this here it should be V rather than I. It should be V rather than I here. So we should have V here. We should have V here. So finally we have V here. And then we can just divide LC on both sides. Divide LC on both sides. So we have a D2V dt2 plus RC over LC will be R over L dV dt plus 1 over LC times V equals 0. Yeah, so yeah, as you know, we can still follow similar procedure, so that this is actually a second order ODE for the voltage, and actually it will be also correct for Q, for I, for VL, for VR, whatever. Yeah, so here, as much as we need to solve this, ODE, we can write the characteristic equation, which is changing the second order to be S squared plus R over L, and then times S, changing the first derivative to S, and then 1 over LC, and then this one to be 1, so it will be like this. This is the characteristic equation, and of course here we will assume delta equals B squared minus 4AC to be smaller than 0. Yeah, we will make this assumption, because if B squared minus 4AC is larger or equal to 0, it is nothing but real root or distinct real roots or repeated real roots, and then the solution will be like exponential decay. So this is what we are looking for. So usually we will concern the case for the delta to be smaller than 0. In this case, we will have a complex conjugate roots for this characteristic equation, and of course S will be 2, and then minus B, which is minus R over L, and then plus or minus, and also, yeah, actually B squared minus 4AC is, yeah, B squared minus 4AC is R squared over L squared minus 4 over LC. And then if we assume this one to be negative, here we will write it as 4 over LC minus R squared over L squared times I, something like this. Yeah, because we need to take the square root of this term. If it is negative, then we just minus another, multiply by another negative sign, and then we have an I here. Yeah, so actually S will be minus R over 2L, and then plus or minus I times we can just divide these two into here. So we have 1 over LC minus R over 2L, the whole term to be squared. Something like this. So we have this is the roots for the characteristic polynomial. So this is the real part, this is the imaginary part. This is the imaginary part. And yeah, if you still remember, as much as we know this complex conjugate root, so let me just this one, yeah, is it here? Yeah. So in this case, we will have V. I'll just say V to be let's say V, which is a constant, oh yeah. So it will be, or maybe you can write it as, exponential to the real part. Real part is minus R over 2L, so we have minus R over 2L times T. And then we will have a C1 cosine omega prime. Omega prime is this term. Omega prime is square root of 1 over LC minus R over 2L whole term square. And of course, we can also write it as omega is 1 over square root of LC. So that omega prime is omega square minus R over 2L square. So it is omega prime T plus C2 sine omega prime T, something like this. If you still remember how to solve the second order ODE. Okay. And of course, as much as we have cosine and sine, we can also write it as a V exponential to minus RT over 2L, and then cosine omega prime T, omega prime T plus phi. Yeah, we have demonstrate this procedure, how to change from this expression to here, so I don't repeat it here. And of course, originally we have the equation for Q, so actually you can still write it for, if we have a d squared Q dt2 plus R over L dq dt plus 1 over L c q equals 0. So we also have a q to be q exponential to minus RT over 2L, and then cosine omega prime T plus phi. So which is actually the same as this solution, q times exponential to minus R over 2LT cosine omega prime plus phi. Omega prime is this one. So as much as you know how to solve the second order ODE, then you will know why it will look like this. Okay. So so this is interesting that if we don't have this R, then the oscillation frequency will be omega. And then if there are some resistance series with this LC oscillator, then the oscillating frequency will be lower than the original case. If R when R is larger, then omega prime become even smaller. So this is reasonable because it is something like originally there are no losses, which is something like there are no friction force, something like that. Then as much as we have some R, it is like there will be some friction force, then of course the frequency will become lower, the oscillation frequency become lower, which is somehow like it becomes slower because there are some loading. It makes the oscillation to be slower. Okay, this is the analogy of the spring mass system. So if we have, if you still remember last lecture, we also have this one. The coefficient, the spring coefficient is K, and then this is the mass, and and this is the reference point, and then this is X. So there will be force F equals minus Kx. F equals minus Kx. And of course, according to the Newton's law of motion, F will be d2x dt squared times m. F equals ma. So a is the second derivative of the displacement. And here we also model the friction force. We also model the friction force, which is like F friction force is minus B times dx dt. So what does it mean? So dx dt is of course the velocity. So it is like if we have the velocity to point to the positive side, then the friction force will point to the opposite side. And if it is point to the negative side, then the friction force will be point to the opposite side. So it matches the intuition for the friction force. And if the velocity is larger, then the friction force will also be larger. Because if you don't move, then there should be no friction force. So it somehow matches the intuition. Of course, the friction force doesn't necessarily to be minus BV, but it is just one assumption. It's just one assumption. And of course, B is the coefficient for the friction force, which is like if B is larger, then the friction force for that material between is strong, or maybe the loss within this spring is larger. So now we can just we can see this is the constant. So this is the force due to the Hooke's law. And F should be let's see, F should be Fk plus F friction, the spring and also the friction. So F is m d2x dt2 equals Fk is minus Kx, and then Ff is minus B dx dt, minus B dx dt. So so we can just move these two terms over. We have m d2x dt2 plus B times dx dt plus Kx equals 0. So we can just divide m on both sides. So we have a d2x dt squared plus b over m dx dt plus k over m times x equals 0. So comparing with the previous case, we have this additional time due to the friction force. And similarly, we can just compare with this one. Let's see here. Okay, comparing these two, so we can change R to be B, and then L to be M, and then C to be 1 over K. C to be 1 over K. So which means that 1 over LC will be M times 1 over K, 1 over M times 1 over K. So it will be K over M. So we will get this equation from the bottom one. Or maybe I can just write it here. Plus R over L dQ dt plus 1 over L CQ 0. Yeah. So if you still remember, in the last lecture we also have this same analogy here. So we can just have this one correspond 1 over LC to K, L to M, so on and so forth. But here we also have R to be B. We also have R to be B here. We also have this one. And of course for this, so as much as we have this solution, we can also get the solution of this second order ODE. So let's see the so we can also get the X to be let's say X exponential to minus BT. We change R to B, and then we change L to M, cosine omega prime T plus phi. And of course omega prime is 1 over LC minus R over 2L squared. So omega prime here should be 1 over LC is K over M. So we have K over M here minus B over 2M squared, and then take the square roots. So we altogether have this expression and also this expression. So this is the analogy between the LC oscillation and also the spring mass system. Okay, so let's take a look at another sample problem. So here it says a series RLC circuit has inductance L, C, and resistance R begin to oscillate at time t equals 0. At what time t will the amplitude of the charge oscillation in the circuit be? 50% of its initial value. So note that we do not know the initial value. Yeah, and of course, Yeah, of course we know we have something like a q equals capital Q exponential to minus RT over 2L cosine omega prime t plus phi. Yeah, so we have this expression. We don't, yeah, it tells you that we don't really need to, we don't really know the initial value. We don't really know what is Q, but it doesn't really matter. We only need to care about this one is 0.5. This one is 0.5, which is 50%. We don't really need to know Q. Actually, we need to know the time t such that this is 0.5, so this is a 0.5 Q, 0.5 Q, which is 50% to Q. So we don't really need to know the Q because we only need to care about the ratio, and the ratio is actually this exponential term. And for simplicity, we just ignore this one. We just ignore this one. So let's see. So here we consider that exponential to minus R t over 2L is 0.5. So we can just take the inverse on both sides. We have exponential to RT 2L equals 2. And then we can take lateral log on both sides. So we have RT over 2L equals lateral log of 2. Lateral log of 2. So we have a T equals 2L over R lateral log of 2. And then we can just plug in the numbers. So we have T equals 2 times 12 milli. And then over R is 1.5. So it doesn't relate to the capacitance. And then natural log of 2. So this number is 11 millisecond. 11 milliseconds. You may also ask why we can just ignore this cosine, but actually we can just have a quick check. Omega prime is nothing but 1 over LC minus R over 2L and then square root. And it will be approximately, of course it will be slightly less than this term, but actually we can just take an approximation. And let's see, L is 12 milli times 1.6 so this is 7,217 radian per second. So the SI unit for omega is a radian per second. If this is F, it is a hertz. The SI unit should be hertz. So if you have a omega prime times T, so it multiplied by 11. So it will be omega prime times T will be 79.3, so which is much larger than 2 pi. So it should be like something like this. We have you have this to be the exponential function. So this is exponential to minus RT over 2L. Of course, this is minus exponential to minus RT over 2L. And actually, it will be something like this. Something like this. So you try to draw a sign, or originally the sign should be from -1 to 1, but it is bounded by the exponential function. And we care about, what we care about is, this is 1, and some point later this is half. Of course, the period may not be the correct because there should be many cycle. There should be, this is 6 point something, this should be, this should be more than 10 period. So this figure is just for demonstration. It is not really correct in this case. But so for this exponential decay sinusoidal wave, it is something like this. It is something like this. Okay, so for part B, how many oscillations are completed within this time? So actually we need to calculate the exact value of this case. So we use this formula, which is 1 over LC minus R over 2L quantity square, and then take the square root. So it is 1 over 12 times 10 to the minus third power times 1.6 times minus 10 to the minus 6 minus 1.5 square over 2 times 12 times 10 to the minus third square. Let's see, this should be 4, this should be 4, this should be 4. So this number will be 7.217 kilo radian per second. And the number of oscillation should be 11 times 10 to minus third power, and then times 7.217 times 10 to the third power over 2 pi. Because you know omega prime times t should be 2 pi. This is the period. This is the angular frequency of the oscillation. This is the period. So t will be 2 pi over omega prime. So actually the number of oscillation is like the time. Maybe I should use t, maybe use t0 here, t0 here, t0 here, t0 here, t0 here. Yeah, so actually this is nothing but t0 over t. So it is t0 over t, which will be over 2 pi times omega prime. So this one will be 12.6 times. 12.6 times. So which means that from 1 to here, there should be a 12.6 times. There should be 12.6 times. Of course, this is not written. It is only more than 2 here. So it should be 12.6. But if I want draw 12.6, it will be very, very dense. Yes. Okay, any questions? Okay. So So here we will talk about something called force oscillation of three simple circuits. In circuit theory, we will call this one phasor. We will call this one phasor. Yeah, when I studied physics in high school, I think I have learned phasor in high school, but of course I don't really know what it really means. Yeah, actually I also suppose you might have learned this before, but yeah, I try to explain why it will look like this. So here we have a resistor, which is the simplest case. Or maybe we can just take a 10 minutes break now.